Hello, this is in response to Minute Physics proof of conservation of energy. I'm posting this to show that there's an actually even simpler way of doing it that is just as general. So the example that I use here is the same as in Henry's video of an object moving in a gravitational field, but the general idea is completely independent of this setting. So if you think of a ball rolling up a hill with a certain momentum, then you intuitively know that the higher the ball rolls, the less and less its momentum will become. So this arrow here represents momentum. And there are just two things that come into play with conservation of energy. Just two simple equations. The first, is the simple observation that the displacement in the gravitational field, dx, is just vertical velocity times the time difference. So this is just displacement is velocity times time. And the other one is looking at not the change in height, but the change in momentum. So this purple arrow here has decreased from here to here, and the change, again, just the vertical change in momentum, dp, what we use here is that this change in momentum is force, gravitational force, times the time interval. So many physicists don't realize that force is just change in momentum. But this is really fundamental and makes many calculations and observations very simple. So you just look at two things. How does the force depend on the displacement? So the relationship between height and gravitational force, usually close to the surface of the Earth, the force is completely independent of the height, but we could very well imagine that at a higher altitude the gravitational force becomes smaller. And we look at the relationship between momentum and velocity. Again, here on Earth, for slow-moving objects, momentum is just proportional to velocity, but we could very well imagine that for a highly relativistic object, we have lots and lots of momentum, but the velocity cannot go beyond the speed of light. So the shape of these curves is completely arbitrary. It could be anything we want. We just look at two things. What's happening when the object is rolling up the hill? So we have an increase in displacement in height, and we just look at the area of this little rectangle here. So this is force times vertical displacement, dx, and we know that dx is just vdt. So we have force times velocity times time, and on the right side, the change or the area of this rectangle is just velocity times change in momentum, well, positive change in momentum, and we know that dp is just force times dt. So we get exactly the same expression in both graphs. So an increase in x makes that the decrease in p is just such the areas of these two rectangles is exactly the same. And that just means that if you imagine these graphs filled up with something, that whatever we put in here must come from here and vice versa. So any change in this liquid on one side comes from a decrease on the other side. And this area, this red area, is actually just the energy. Here we have potential energy. So if you imagine the force to be independent of displacement, this is just force times height, that is potential energy. And here we have kinetic energy. So if you imagine that this would just be a straight line. So there you have it. A nice simple proof of conservation of energy. Thanks for watching.